Hello. Today we're going to be going through a couple more topics dealing with vapor pressure, water, and how we can automate some calculations. And to do that, we're going to go through a couple of problems. So let me go over to the whiteboard here, and we'll start off with this first one. So as you can see, I've drawn a diagram of a container with water in it. As you can see, the container is 0.1 meters cubed in volume. We have 1 kilogram of water occupying the space. And the system is at 298 Kelvin, 101,325 pascals, which is standard conditions. Now, what we want to find is at what final temperature are we going to get a final total pressure of 200 pascals. So, in order to do that, let's just move over here. We'll move down a bit. So, a couple of topics that we can be familiar with that can help us out with this problem is knowing what this problem entails in terms of what equations are we going to have to use. So one for sure is going to be, it'll come straight out of our phase diagram. So let's draw this out. Draw out our little phase diagram. There you go. Solid, liquid, gaseous. And so a big takeaway from this is knowing what happens along this line here. This is our liquid vapor and liquid water. Sorry. This is our liquid water and vapor water. This line will separate out the two. And what lies along this curve is something that we call the equilibrium pressure. Equilibrium pressure. Or the pure component saturation vapor pressure. Saturation vapor pressure. Pure component saturation vapor pressure. And what that is if we look back up at our diagram here. Oh, hi. If we look back up over here in this diagram, we can see that we have some liquid water here and vapor water in the headspace. And so what that term tells us, the pure component saturation vapor pressure, is that in this container, we can assume that the pressure of the partial pressure of water in air is going to be equal to the saturation vapor pressure of water at the interface or in this liquid phase. So this is a big thing that we will have to keep an eye on as we work through this problem. Another thing that we want to take a look at is going to be somewhat more simple, and that is the ideal gas law equation, PV equals nRT. And we're going to use this for the partial pressure of air. Because remember, in this closed container, we didn't say anything about evacuating all the air out of the space. We just said that there is a closed container with water in it. So we are assuming that air is also part of the system. So for this, we can derive out that pressure is equal to nRT over V, which is a lot more simple, but it'll be necessary. And then we want to focus on a new equation here. And that is something that we call the Antoine equation. Now, you may have heard of the Clausius-Clapeyron equation, which is something that we use for some first-year chemistry, high school chemistry things. However, if we want a more accurate read, we want to use the Antoine equation, which goes like this. It is the log base 10 of pressure is equal to some constant A plus, or sorry, it'll be minus here. Some constant A minus B over temperature plus constant C. And A, B, and C are constants that are experimentally defined. Regressions have been performed through multiple data points in order to find these constants. So we will look that up in a table when the time comes to that. But in order to get rid of this log here, I'm going to put this to the 10 power. I'm going to put all this to the 10 power. And going to be pressure is equal to 10 to the A minus B over T plus C. Boom. So that'll be our third equation. So now let's start piecing this together. I'll use this area over here. Let me redraw kind of a 2D model of this diagram. There we go. So we know that we have some water in our system here. We just draw this a little bit. This is going to be liquid water at the base. This is 1 kilogram of liquid water that we have in this container. So we know here that we have liquid water. And in this headspace, we have the partial pressure of air and the partial pressure of water. So we can say that at any point in time, the total pressure at some temperature is going to be equal to the partial pressure of air at that temperature plus the partial pressure of water at that temperature. So we can start plugging and chugging in some values here. We came back from earlier that we know that the partial pressure of water and air is equal to the saturation vapor pressure of water. So let's make that our first substitution here. So this is just going to be equal to P sat H2O at the temperature. And we can, this is a lot better than just using the vapor pressure of water at some temperature, because we can grab this value from this curve right here. So it is a lot better to use the saturation component as opposed to this vapor pressure that we have in the atmosphere. The next thing that we can kind of plug into, remember I said earlier, we're going to be using the ideal gas law equation. So for this one, we are going to plug in moles of air times R times T over the volume of the vapor phase. Notice how I said the vapor phase and not just the volume of air. Because remember, we have to take account for the volume that the vapor phase takes up. So this is going to include the volume that the partial pressure of water takes up and the partial pressure that air takes up. We're going to combine these values and use that for this vapor pressure. And we kind of know what that is already, because if we look over to our givens, we see that we have 1 kilogram of H2O. This entire container is 0.1 meters cubed. If we run some calculations, we actually find out that the liquid phase only takes up 0.001 meters cubed, and actually that the vapor phase takes 0.099 meters cubed. So we actually can get that volume from there, and this is the volume we'll be using for that. But as you can see, we now have a new equation for this vapor pressure. Oh, sorry, for the total pressure. Now, we only have really one big glaring issue with this, which is we don't know what this is. We can go back to this graph here, but we don't really have any readings to kind of determine what this saturation vapor pressure is. And that's actually where our Antoine equation is going to come in, right over here. Because that is going to tell us what we have to plug in for here. And then we can solve for the final temperature in that case. So if we look at a table of values for the Antoine equation, it'll be in degrees C and millimeters of mercury. these are the values that you're probably going to get when you look at a table. So actually, I can pull up Wikipedia here. Let me Antoine coefficients for water. Where is it? Where is it? If we look down here, we see that our temperature is in degrees Celsius and our pressure is in millimeters of mercury. But we do have these values here. So we can use these. We can use those, but we just have to make sure that we convert degrees Celsius into Kelvin, or we have to go the other way around. It'll depend on how we want to convert it. And millimeters of mercury have to be converted into pascals, because that is essentially what we are using in our equations here. So we can do one of two things. We can take this equation here and we can convert from degrees Celsius into Kelvin, in which case we just need to add 273.15. And then millimeters of mercury, we're going to have to use that conversion factor for this pressure. If it's in millimeters of mercury, we have to then multiply by the conversion factor. So let's just take a look at what that's going to look like. So get this over here, moles of air times R times temperature. And if we want to keep this in Kelvin, I think it might be a better idea to just convert this into Kelvin. I feel like that would be a better idea here. We have that. So now we are going to put this in brackets, because why not? Make it a little bit easier. So 10 to the A minus B over T plus 273.15 now plus C. So now this is in Kelvin, right? And since this pressure is in millimeters of mercury, according to what our constants that we are going to use, we will multiply by a conversion factor that we know, which is that 760 millimeters of mercury is equal to 101.325 pascals. Or rather, this should be flipped around because we are converting the other way around. So let's just do a little switch D over here. Oh my gosh. So we want pascals on top. 101.325 pascals over 760 millimeters of mercury. And now essentially what we have done is we have derived our equation for finding this pressure that we have at the temperature. But you see how this is a really, really convoluted equation, and it's going to take a lot of algebra and a lot of calculating using your standard calculator to set this pressure equal to the pressure that we want, which is equal to 210 to the third pascals. We have to plug this in for the pressure, and then we have to put in all our constants. And then we're going to have to solve all the way over and make sure we isolate our t. It's just going to be a lot of work. So what we instead would like to do is we're going to take this equation and we will automate it using Python. So let's actually get into that next. So now that we've gone and kind of simplified out the equation we're going to use, let's actually start importing that into Python. Forgive the bit of an outfit change. It is game day today, so I had to get into a little bit of the spirit. So first let's start by importing something we're going to be using later on, which is going to be from the SciPy library, scipy.optimize. We're going to import root. And what a root does, it takes a function and finds its zeros. So say if you had something like a sine function, it'll give you an array of all the values that makes it 0, or if you make a guess, it'll give you a value nearest to that guess, which will give you a 0. So this is going to be important for us because we want to find the temperature values that make a certain equation 0. So we'll take a look at that in a bit. First, let's go find our constants from the Antoine equation. So A is going to be equal to this one right here. C control V. B is going to be equal to right there. And notice how even though that it's giving us a certain temperature range, we're assuming we're kind of working in the realm of this range from 1 to 100 degrees. Since any point after 100, that is of course the boiling point, and we are probably not going to get that high. So we have our A, B, and C. So now we can take a look back at our whiteboard, and this is the part we're looking at here. That is our Antoine equation that we are looking at. So let's go and define a function. I'm going to name this PSAT for saturated vapor pressure. Define PSAT as a function of T, where we will be returning that equation that we had written down. So 10 to the A minus B divided by, and since we are working kind of backwards in a sense, we are inputting a temperature in terms of Kelvin, and out of that we want to put the Celsius value into our function. We're kind of going to work backwards. So we're going to go T minus 273.15 instead of the other way around. So let's go T minus 273.15, and we're going to add C to this, plus C. And that's our equation more or less. Do I need another parentheses here? I don't think so. Yeah, don't think so. So now we have this, but remember, if we put it in this way, we are going to get an output of millimeters of mercury. And we want it in pascals since those are the units we're going to be working with. We got to keep our units constant. So let's multiply this by the multiplication factor we have to use. So 101,325 divided by 760, and that should give us an output in millimeters of mercury. And we can actually run this. Let's go open a new cell down here. We can actually run this formula and double check it, see if we have any mistakes. So let's go PSAT, say 300, let's go 315, or no, what do I have to put in here? Plus 100, 300 degrees, let's go. PSAT is not defined. Well, that's strange. Oh, is it not on the local? It's possible that it's on local. Let's try here in the local frame of view. We're going to go PSAT of 300 degrees. That is an extremely large output. I'm not sure why we're getting that. Let's see. Maybe if this is it. Yeah, that's a lot. That's a lot more like it. So now we know that that function works. Right? And now that we have that, we want to start defining some of the things that are going to come out of this part, where we have, this is the pressure of air at that certain temperature. So let's actually start writing down some of the variables you're going to use. Of course, first we need our R, which is going to be 8.314, since that is universal gas law constant in terms of joules per mole Kelvin. We're going to have our R. What's another constant we need? We're going to have our T initial. We will need that because that's going to be 298. We'll need that a little bit later on when we calculate another one of these variables. We're going to have our initial pressure, which is going to be 101,325. And I'm going to put little dots here. Ooh. Put little dots just so that we solidify the fact that these are floats and not integers. Just make sure that the compatibility will work later on. While we're here on pressure, we can put in the final desired pressure, which is going to be 200,000 dot. Why is that happening? No, thank you. And now, what else do we need? Let's see. We got our R. Our T is going to be defined. Let's see, our V. So the volume of the vapor, remember, we calculated this out. We have 0.001 meters cubed of that water, whereas we only have, and then due to that, we have, one full, what's it? Let's see. We had 0.1 1/10 meters cubed. So if that is 0.001 meters cubed, then of course we're going to have a volume. The volume of the vapor is going to be 0.099 meters cubed, just making sure that we're getting to that full 100%. And so VVAP is going to be ending up as 0.099 meters cubed. So that's another constant that we can put in there. After that, we also want to take a look at the last big point, which is going to be this right here, our moles of air. So let me actually draw out how to derive this. So we know that from PV equals nRT, we know that N is just N equals PV over RT. However, the thing that we need to realize is that this is moles of air. And the moles of air in this system is going to remain constant. We are not reacting moles of air. We are not changing moles of air. It is a closed system where air was present before and air is still going to be present afterwards. So we can go and define this a bit further. We're using the initial pressure times the volume of the vapor divided by rate law constant times the initial temperature. Because we can use these initial ones because the initial is going to be more or less equal to the final in terms of moles. So let's write that out too. So N air is going to equal, let's go pressure initial times VVAP and then divided by R times T initial. Simple as that. And now we should have all the variables we need to calculate our pressure of air. So let's go define a new function called P air with a variable T. And this is going to be returning a value of, it's going to be PV, let's take a look actually, jog our memory. It's going to be nRT over V, right? So it's going to be n underscore air times R times T, which is going to be our variable that we are defining right there. And that's going to be divided by the volume of the vapor, VVAP. And that should give us our pressure in air. We can also check that one, but it's probably going to work, so I'm going to leave that alone. Now the last part is to kind of piece it all together. Now, when we look back at our whiteboard, full screen you. When we try and find roots of, say, a quadratic function, right? Sorry. When we find roots of a quadratic function, we have something in the form of, we have something in the form of ax squared plus bx plus c equals 0. This is important. We have to set these equal to 0 to find the values of x that make the equation 0. Same thing here. If we want to find the roots of this function, we need to have the left side of our function be 0 and the right side of our function have all of the things that we have to calculate. So we're actually going to bring our desired pressure value all the way over here and subtract it. Right? And now on this side we have 0. So that facilitates us to find the root. Essentially is what that is doing. So let's define now P, I'm going to call this P total, P tot, as a function of T. And what this is going to be is it's going to return a value, and it's just going to be it's going to be the other side of that equation. One side 0, and then the rest has all the stuff that we've already gone and calculated here. So it's going to return P sat T, right, plus that P of air of T, and then minusing our final or desired value. And now when we do this, we have essentially set up an equation in which we can find the roots, and the roots are going to be the values of temperature that make that 0. So that's where we are going to find this function to be really, really handy. It's going to find all the zeros for us in terms of, so actually, let me just show you instead. I can type it out a lot better than I can explain it. So if we take the root of our P total here, right? And then we just are going to make some sort of guess. Say, okay, 300 Kelvin, right? If I hit enter, boom. It gives me all this stuff. It says the solution converged, which is good. You can make more educated guesses than just 300. It's just something I'm throwing out there because it doesn't necessarily matter too great. But you can see that we have this output of an X value, 365. And that is actually going to be the temperature we want to bring our system up to in order to have it at that final pressure that we want. It is the root. It is the 0 in this sense, right? So I guess if you want to think about it a bit more mathematically, if you have, say, a parabola whose zeros you're trying to find, you have one here, you have one here. Essentially, that is what we did. We found what this value is in the context of our equation. So now you saw how to optimize and automate using Python for that specific problem. So now I've drawn out the second problem we're going to look at here, and as you can see, there are a few differences. So first off, we don't know the volume of this container. We don't know any of the headspace. We don't know how much original water is in this container. We just know the fact that we have some container of some volume with some amount of water in it. We also don't know what the initial and final temperatures of this, well, we can kind of figure out the final temperature, but for purposes of this right now, we don't really know what this temperature is. So this is also 2 question marks that we might have to solve for using some Python code, but let's first derive the equation given the information that we have. As you can see, we are working with the same final pressure, still 200,000 pascals, and now we are looking at an instance where we want the final mole value of water in the vapor phase. We want that to be 0.3 moles. So we can go through and we can use PV equals nRT to sort of derive an equation and try and solve this out. So to solve for n, we need to shove RT over to this side, and we're going to do that by dividing. So what we get here is now NH2O is going to equal the pressure of the water in the vapor phase. So that's going to be the saturation vapor pressure. But for now, I'm just going to put PH2O, the partial pressure of water, times the volume of the vapor phase, over universal gas law constant R times T. Now, realize that we don't know the volume of the vapor phase and we don't know the temperature. So now we're going to have to use some Python code to go and figure this out. So now that we've derived that equation that we're going to be using to find out our unknowns, let's start coding it into Python, and so we can automate it using the root function once more. So let's start off by defining our function here. I'm just going to call this function, F-U-N-C, why not? And this time the input is not just one thing. It isn't just temperature. It isn't just the total volume. Instead, it is both of these things. And so what we're going to input is something known as a vector, right? So the input of this vector is going to be unpacked within this function, where we're going to put vtotal and temperature. Let me just move this here. Vtotal and temperature, these are going to be equal to our vector. Right. Now, the first equation that we want to use to try and kind of input into our optimization functions, we want to make sure that we have that total volume in there. And so another thing that we don't really know here is that vaporization volume, right? We don't know our total volume, and we don't necessarily know what our vapor volume is here. And so let's go ahead and say that our VVAP, in this case, this is different from the last case, our VVAP is going to be equal to our total volume minus our mass of water divided by 1,000. And we do that because we know that the density of water is 1 kilogram per liter, or 1 kilogram per 1,000 milliliters. And so in this case, we can go our mass of water. You see that I put this over here as 1.0 kilograms already. So our mass of water, let's reference that, divided by 1,000. And that'll give us our volume of the vapor phase. Now, there's also another thing that I want to point your attention to. Over here, we talk about this. We have that moles of H2O. However, if you remember from the last problem, we don't only have water in that atmosphere. Rather, we have a couple of things. We have water, of course, but we also had air. We also had air in there. And so we also want to account for the fact that this air is in our system. And so the way we calculate that air is the same way we calculated the moles of air last time. So if we scroll up, we see we have this equation here. So we can copy and paste that down right there, and then air is going to be equal to that. So now we see that we have our volume of the vapor phase being referenced in this equation here. And so using this, we can now return our optimization functions. So return, and since there's multiple, we're going to create a list of them. Now we do these optimizations in the order that we input our vectors. So since we have our total volume first and then our temperature second, we have to go ahead and make sure that the total volume is the first part of our function. So let's actually just go ahead, and that total volume function, well, that's just going to be coming from this equation right here, right? That's going to give us our optimization for this volume. So let's go back and let's type this out. So on the top, we had the saturation vapor pressure of water. Remember that when equilibrium conditions hold, the pure component saturation vapor pressure is equal to the partial pressure of water and air. So we can just use this reference here, Control C, and have that there for our pressure. Now the next thing that we need to put in there is going to be the volume of our vapor phase. So VVAP is going to be right there. And then we're going to divide this by R times T. Now remember, whenever we optimize something, we always want to make sure that one of our sides is equal to 0. So we're going to bring NH2O over here, and we're going to end up subtracting our moles of water so that we can optimize for the volume. Optimize for the volume. So let's go and subtract NH2O. I'm just going to go here. And that should give us our total volume. That's going to be our first thing. Now, the next thing we want to optimize is our temperature. However, if you may remember, we've already done that. We just optimized this total function here. So we could just take this function, Control C and Control V. It's the exact same thing, and we can use these functions to go ahead and find our roots. Make sure not to take your bracket off. So now let's go and have our root function. We want to optimize func. And our guesses, since we have two unknowns, we want to make two guesses this time around, right? So let's go ahead and create a list. And let's say our first guess, we're just going to guess what we did last time, which was 0.1. That was the volume of the container we had last time in the last problem. And we found out from last time that our optimization here for temperature is around 365. So let's actually just go ahead and plug that in, 365, and then shift enter, see if this runs. Yeah. So it looks like our solution did converge, and now we have these values over here for our total volume and our temperature. And so this is how you would use Python to go ahead and automate something like that, a question with multiple unknowns. We go ahead and use a vector, we unpack that vector, and then we use functions to go ahead and optimize the things that we don't know. Thank you for watching. I hope this has been helpful. Have a nice day.